Hello, welcome back to Mrs. Ogram's Maths. We are going through the worked solutions for the D&D Resources, and we're on Practice External Assessment number 6 from the Complex Numbers booklet. So again, a thank you to D&D Resources for allowing me to use their materials in this way. I have put a link to their website in the description for this video, so you can go online and order physical copies of this book. When it comes to maths in particular, I highly recommend that you do this stuff on paper and not just straight off of a screen. Because a lot of the stuff you can't type out so easily. Okay, so question 1. We've got that x minus 2 is a factor of this polynomial, which if it is a factor, it means that we can put the 2 into it and we'll get an answer of 0. So we'll have a 2 in every place where there's an x, like this, and set that equal to be 0. Tidying that up, we get 8p. We've got 2 squared is 4, and then times the 3 is a 12. Then we have minus 2p plus 4 equals 0. So collecting those up, we have 6p minus 12 plus 4 is going to be minus 8. So 6p is 8. P is 8 over 6, or 4 over 3. Part B, we've got w. We need to find w to the minus 2 and put it onto the Argand diagram. So w to the minus 2 is 1 over w squared. So that's 1 over 0.1 minus 0.3i squared. Now that much we can do on the calculator, save ourselves a bit of effort. So 1 divided by 0.1 minus 0.3 I all squared is equal to minus 8 plus 6i. And then popping that onto the Argand diagram, we go minus 8 in the real direction and plus 6i in the imaginary is going to be just here. For part C, we've got one solution is z equals minus 3, which means if we put minus 3 in the place of z, this equation will be true. So let's start with that. And then that'll help us to work out the A. And then we can go ahead with finding the other solutions. Okay, so minus 3 cubed is minus 27. Times by 4, that's minus 108. Minus 3 squared is 9, so this is 9a. Minus 3 plus 21 equals 0. Okay, so minus 108, take off 3 and add 21. So 9a will be equal to 90, so a equals 10. Now for the next part, let's write in what our full equation is. Now we know that a is 10. We also know that if minus 3 is a root, then this tells us that z plus 3 is a factor. So we can use that to find the other factor of this polynomial. And there's a couple of ways that you can do this. You can do it by inspection, by taking a look. You can use algebraic juggling. You can use long division. I'm going to do it by inspection. So looking at what we would need in the next bracket to make that true. So it'll be something z squared, something z, and then a constant. Now to make 4z cubed, we need to do this z here times by this z squared here, so we'd need a 4 in front of it to make that true. Now the next bit is to look at the constant term. So this constant term here will be 3 times by whatever is in the constant term there. So to make that be true, then that needs to be a 7. So this will be a plus 7. missed there. Okay, now we just need to work out what goes in place of the z. For that, we can either look at the z terms or we can look at the z squares. I'm going to look at how to make a z. So to make a z, we would do z times the 7 here, and we would do 3 times whatever goes in this z here and add them together. So we would have 7z plus something z has to be equal to 1z over here. So that gap has to be minus 6. Now that gap is made from doing 3 times that space that we have there. So this one must be a minus 2 to make it into the minus 6. Okay, so let me pop in a minus 2 just there. Okay, we'll just tidy this away now. So now we've got the quadratic factor, we can solve that. So we're setting 4z squared minus 2z plus 7 equals 0 to find our other two roots. So z is minus b, which is 2, plus or minus the square root of b squared, so that's 4 minus 4ac all over 2a. Which is going to be 2 over 8 at the beginning part, so that'll be 1/4, plus or minus, and then we've got 16 times 7, and we're doing 4, take away that. So this will be the square root of minus 108 over 8. Now, if we include the 8 into that square root and make it a 64, then we can do some simplifying. Let's see if that helps us at all. Okay, so now we've got 1/4 plus or minus the square root of minus 27 over the square root of 16, so that'll be just a 4. Minus 27, we can take out a square number of 9 there. So we've got 1/4 plus or minus. If we take out the 9, make 27 9 times minus 3, and bring the 9 out of the square root, we've got a 3 with a 3 left over. Taking out the minus 1 gives us the I, and this is all over 4. You can also check that one on your calculator using equation solver. So if we do equation solver for a polynomial quadratic, of degree 3, and put in the cubic that we had to begin with, then we've got 4 in the place of A. We had a 10 in the place of B. We've got a C is 1 and D is 21. We can set up our options to show us the complex roots and then solve it. And you can check that these answers match what we've got just here. They are in decimal form, but those decimals do work out to be the same as this. Okay, for part D, we need to do some solving here so that we can then work out the argument of z. So if we first try and solve this equation here so that we can work out z, we'll be able to find the argument. So let's work that through. If we've got 2z, and then on the top we have 3iz minus 6i is equal to 5 plus 9i, and then times it by the 1 plus I that was on the bottom there. So let's start with that. 5 plus 9i times by 1 plus I is going to get us minus 4 plus 14i. Now let's take this 6i over. We'll have, and actually I'm going to factorize out the z as well at the same time. So 2 plus 3i and then we'll take over the 6i. If we take that 6i and bring it over here, we'll add another 6i. So that'll be minus 4 plus 20i. So then z will be minus 4 plus 20i divided by 2 plus 3i. And again, we can reach for our calculator for that one. 2 plus 3i, which gets us 4 plus 4i. Now the argument of z, we just need to have a think about where that would be on the Argand diagram. So a plus 4 along here on the real axis and a plus 4 on the imaginary axis, and working out what angle that makes here, well, that is an isosceles triangle, so it's 45 degrees or pi by 4. For part E, we're working with modulus, and if we do the modulus of A over B, that's the same as doing the modulus of A over the modulus of B. So the modulus of W, for part I this is going to be the modulus of K plus 3I divided by the modulus of 2K minus I. Okay, now modulus means we do the square root of, I'm going to make this a bit bigger actually, the real part and then the imaginary coefficient. They both get squared, added together, and then square rooted. And then on the bottom, same thing. So the real part is 2k being squared. Make sure you square all of it, not just the k. And then the imaginary coefficient is a minus 1. So we're setting this to be equal to 2 from our equation. We can square both sides so that we get rid of the square root symbols. So we end up with k squared plus 9 over 4k squared plus 1 is equal to 4 by squaring through and getting rid of those square root symbols. Okay, now let's carry on with our rearranging. So k squared plus 9 is equal to 4 times 4k squared plus 1, which is 16k squared plus 4. So if we take the 4 over to the left, 9 take away 4 is 5, and then 16k squared take away a k squared is 15k squared. So k squared equals a third, and k is equal to plus or minus the square root of 1 over 3. That usually gets written as plus or minus 1 over root 3 because square root of 1 is 1. Now for part 2. Give the complex numbers w in the form a plus bi. Now if you have the most up-to-date graphics calculator, you can just type this into your calculator and you substitute in the values of k that we just worked out into what w is, and it'll give it to you. My calculator doesn't do that, so I will show you the long way to go about it as well. So just remembering up there, we've got that w is k plus 3i over 2k minus I. So when k is equal to the positive answer we just had of 1 over root 3, we'll have that w is 1 over root 3 plus 3i over 2 times 1 over root 3 minus I. We'll just tidy that up to be 2 over root 3. Now we'll need to rationalize the denominator, so times by 2 over root 3 plus I over 2 over root 3 plus I there. And then multiply out. So 1 over root 3 times by 2 root 3 on the top gives us 2 over 3. Then we have 3i times 2 over root 3 is 6i over root 3. Then we have I over root 3, and then 3i times I is going to be 3i squared. I squared is minus 1, so we turn it into a minus 3. All over 2 over root 3 times 2 over root 3 will be 4 over 3. And then minus I plus I, because when we do the conjugate there, those will have minus I times plus 2 root 3, and then plus I times 2 root 3. That will cancel, leaving us just with minus I times I. So that's going to be minus I squared. Now I squared is 1, so this is a plus. So we got minus I squared. We're turning it into minus minus 1. So that is going to be a plus 1. Okay, so 2/3 minus 3 is equal to minus 7/3. And then we have a 6 over root 3 plus a 1 over root 3, so that will be plus 7 over root 3i. And on the bottom, 4 over 3 plus 1 is 7 over 3. So 7 over 3 here, that cancels into minus 1. And on this bit here, I'm just going to do it off to the side a little bit. So it's 7 over root 3 divided by 7 over 3. That's the same as if you times by the reciprocal. So the 7's cancel, and we have 3 over root 3, which you would then rationalize the denominator again. So we times it by root 3 over root 3. And we end up with 3 root 3 over 3. The 3's cancel, so it's just root 3. So we end up with plus root 3i. Okay, now let's see if we can do the next bit without having to go through absolutely everything there. We can just switch around some signs. So when k is equal to minus 1 over root 3, let's see what that does then. So looking up at where k appears in this, so it was the k that came at the beginning. So now the negative parts of this would be just here and here, here and here. So then this bit times by this bit, that would still make a positive, so that stays as a 2/3. But this bit times by this bit would go to negative, and this bit times this bit would be negative. So that's these parts in the middle. On the bottom, the 2 over root 3 bit, it will be a negative times a negative, so it'll still be a positive. Okay, so the only bit that's changed is the bit to do with I, the complex, the imaginary part. So this bit here is where the sign will change, so it'll change on this bit in our final answer, but the numbers themselves don't change, so we've just saved ourselves a little bit of effort there. So when k is minus 1 over root 3, w will be minus 1 minus root 3i. But if you can get your hands on the most up-to-date version of the calculator, you can skip all of that and go straight from knowing what k is, substitute it in on your calculator and get to the answer. Okay, finding the modulus of 2p over q for question 1. That's going to be the modulus of, well, 2p is 6 minus 2i, and q is 1 plus I. So this will be the modulus of that division there. So 6 minus 2i divided by 1 plus I is going to be the modulus of 2 minus 4i, which is equal to the square root of 2 squared plus. So that comes to the square root of 4 plus 16 is going to be 20. Now, if we're simplifying surds, we take out square numbers where we can, square factors of that. So 20 is the same as doing 4 times 5, which is root 4 times root 5, which is 2 root 5. Now for part B, And on this one, we are going to rationalize the denominator because we want it in a form that doesn't have surds on the denominator. In fact, it doesn't have a denominator as such. So we're timesing it by 3 plus root 2. That sort of opposite version of the denominator where the surd gets turned into its opposite. So 7k times 3 is going to be 21k. Then we have 7k root 2. And then on the bottom, 3 times 3 is 9. If we do this and we do this, they'll cancel out each other. So we just are left with multiplying this one. So that's minus root 2 times root 2, which is 2. So we have 21k minus 7k root 2 over 7. And we can simplify that. 21k divided by 7 is 3k, and 7 over 7 is 1. So it's just like this. And we just check we are in the form that it asked for, where we have something k plus something k root 2. For part C, we need to get this expression into a more standard looking quadratic. And then we can find the discriminant and set it equal to 0 to make one repeated solution. So let's expand that bracket. On the left, we've got x squared plus 4x plus 4 is equal to kx minus 3. So then x squared plus 4 minus k will be the coefficient for the x, and then 4 plus 3 for the constant, like this. Then we're looking for one repeated solution, which means that the discriminant has to be equal to 0. So then the discriminant on this one, b squared, that's 4 minus k squared, minus 4 times 1 times 7 has to be equal to 0. So 4 minus k squared minus 28 is 0. 4 minus k squared is 28. So 4 minus k is plus or minus the square root of 28. Minus k would be minus 4 plus or minus the square root of 28. So k would just be 4 plus or minus the square root of 28. And then looking at, we need it to be in this form here. We'll just tidy that up. So we've got 4 plus or minus, 28 can be divided by 4. So if I just do that over at the side here, so 28 would be the square root of 4 times 7, so that's 2 root 7. On part D, we've got a little bit of work to do in sorting out these bits and making things equivalent so we can work out the values of A and B. So let's start by rationalizing the denominator on the left. So ai to the 9 minus I to the 4 over 2 plus I. We're going to times it by 2 minus I over 2 minus I. Before I do that, let's just tidy up what's on the front, on the top of that fraction. So I to the power of 9 is going to be a positive I. So we can just do that as a times I. And then I to the power of 4 is 1. So we can replace this I4 with a 1. Okay, now multiplying across, we will have 2ai minus 2. Then ai times minus ai squared is minus ai squared plus an I. And on the bottom we have 4 minus I squared. So we've got a minus 2. The I squared with this a just here, so the I squared becomes a minus 1, times by the minus there makes it a plus a. I'm getting the real parts out first. Then the imaginary, we have 2ai plus I. And on the bottom, I squared is minus 1, So if we do minus minus 1, we've got 4 plus 1, which is 5. Now let's go back to here and compare it to the 3 plus bi. So for the real parts of that, on the left, on this bit, we've got these are the real parts. So a minus 2 over 5. And the real part in the 3 plus bi is the 3. So then a has got to be 3 times 5, which is 15, and add on the 2, so that is 17. And the imaginary parts on the right, on this the left-hand side of the original equation, we've got that's the imaginary part. So we have 2a plus 1 over 5, and the imaginary part on this is b. So the a we just worked out was 17, so 2 times 17 plus 1, and then divide it by 5. So b is 7. For part E, we are going to set z equal to x plus iy. So then on the left, we have the modulus of x plus iy plus 1 is equal to x plus iy plus 5 plus 6i. Okay, modulus means we're going to do the square root of the real part, which is x plus 1 squared, plus the imaginary coefficient squared. That will be equal to x plus iy plus 5 plus 6y. I'm actually going to rewrite that to collect up the real terms together, so x plus 5, and the imaginary terms y plus 6. Okay, now let's square both sides. Now think about this as being x plus 5 plus y plus 6i, like this, and then we'll square that so we can treat them like two terms, make it a little easier in our working out. So this will be x plus 5 squared plus 2 lots of x plus 5 y plus 6i plus y plus 6 squared I squared. Now that saves us a little bit of effort because we can notice that on the right hand side we have an imaginary term, but on the left hand side we don't. So on the left, if we're just looking at equating imaginary parts, we would have 2x plus 5 y plus 6 is equal to 0. That gives us solutions of x equals minus 5 and y equals minus 6. And for each of those two possible solutions, we need to find the corresponding y or x that would go with them. So if x equals minus 5, looking at this line here, we would have x plus 1 is 6, or no, wait, it's a minus 5. So minus 5 plus 1 is minus 4, and then square it, we get 16 plus y squared is equal to, well, minus 5 in here, plus 5 is 0, so we'll just have y plus 6i squared. Well, I squared is minus 1, so that is going to be minus 1 and then this squared. So that's minus of y squared plus 12y plus 36. So putting that minus through there. And bringing all of this right-hand side over to the left, we would end up with 2y squared. Then we've got a plus 12y, and we have 16 plus 36 is equal to 0. Now if we try and solve that, we can use equation solver at this point. We've got a polynomial with degree 2. The a is 2, the b is 12, and the c is 52. And we solve, and you can see that this has complex roots, which is not sufficient at this point because we need y would be a real number to be able to put it into Z and make it a complex answer. Now this is showing me up as complex roots because I previously had my calculator settings, let's just go back a step, to show that we were doing it in complex mode. If you didn't, and this was just showing it as real answers only, and we hit solve, you'd see there's no real roots. Okay, so this one doesn't work as a solution. No real roots. Okay, so back to if y is minus 6. From this bit just here. If that were true, and again we go back and we pop it into this line up here, we can work out the corresponding x. So if y is minus 6, we've got x plus 1 squared plus 36 is equal to x plus 5 plus, well, minus 6 plus 6 is 0i, so that's going to have nothing there. It'll just be that bit squared. So we've got x squared plus 2x plus 1 plus 36 is equal to x squared plus 10x plus 25. So the x squareds cancel, and we've got, let's bring the x's over to the left, so 2 minus 10 will be minus 8x, and then 25, let's go back to this, so 25 take off 37 is minus 12, so x is 12 divided by 8, 1.5. So we have got a solution there. Now just don't lose track of what we're doing for this question. We're trying to solve for z up at the top just here. So our final stage is to write what our answer for z is. So z equals x plus iy, so that's 1.5 plus the y is minus 6, so that'll be minus 6i. Okay, for question 3, we're solving this quadratic, so I'm going to head to quadratic formula because that's what most people are comfortable with. You could also do completing the square. Right, so x is equal to minus b, which will be 8px plus, or sorry, just the b, 8p plus or minus the square root of b squared, which will be 64p squared, minus 4 times a times c all over 2a. So 8p over 2 is 4p, plus or minus, we're going to have the square root of, it's going to be 64p squared, take off the other thing there, so 4 times 18 is going to give us 72p squared, so 64 minus 72 is a minus 8p squared. That is all over 2. Now if we sort out what's inside of that square root, to square root the p squared, we can just bring out the p. To square root the 8, we can take out a 4. This would be 4 times, or sorry, minus 4 times 2. Now the 4 we can bring out and make it a 2. The minus comes out and becomes an I. So then we're just left with this being root 2i all over 2. So tidying that up, we have 4 plus or minus, the 2's cancel, so we've got p root 2i. It's a little bit weird to write it that way round. We usually put the number first, so that's root 2pi. Okay, for part B, we've got this division to do and then convert it into rectangular form. Since this is only an achieved question as it's a part B, I'm going to do that on the calculator. So what I'm going to need is some options of what we can put in here. So we've got 6, and then sys is using this little symbol just here, the little angle formula. So we just press shift and then this button. And then we've got pi divided by 15. That's going to be divided by, in fact, I'm just going to put brackets around all of it just in case, just to make sure we've got that division happening correctly. Okay, so then we will divide that by 1 sys of 2 pi divided by 5. And it gives us our answer straight away in rectangular form. If I needed that in polar form, I can do a conversion using this button here. That would turn it into polar. But the answer happens to, the question's happening to ask for it in rectangular form anyway, so that first default answer there is correct. So 3 minus 5.2i, or if I want to be a little more accurate, 5.196i. Okay, we've got a purely algebraic question for part C. Let's start by trying to put this into the same denominator that we have on the right-hand side. So if this is all going over x squared minus 4, x squared minus 4 is made up from doing x minus 2, x plus 2. Which helps us to see what we've got to multiply each fraction by to make it over that denominator. So for the px1, we've got the x minus 2, the x plus 2, we've got to times it by the x minus 2 to make that be equivalent. Oops, let's just fix that up. For q, we've already got the x minus 2 on the bottom, so that gets times by the x plus 2. And then the r, we've already got the denominator as we want it, so that doesn't need to change. It's just x squared minus 4. Okay, now multiplying that through, we will have p times x squared minus 2x plus q x squared plus 2x plus r is equal to 8x minus 3. So now looking at the x squared terms, we have a p x squared plus a q x squared, and we have nothing on the right hand side, so 0 x squared. So p plus q has to equal 0. Looking at the x terms, we have minus 2px plus 2qx is equal to 8x. So minus 2p plus 2q is equal to 8. That gives us something we can solve using simultaneous equations. So we've got two unknowns, and the first one is the coefficient is 1, 1, and then the constant is 0. Oops, not finished yet. And then the second one, we've got a minus 2, a 2, and equal to a constant of 8. We solve that. We've got p is equal to minus 2 and q is equal to 2. And then the last bit is for r. That's looking at the constants of this equation up here. The only constant we've got on the left-hand side is r, and on the right it's minus 3. Okay, for part D, first of all we need to express this bit in polar form so that we can use de Moivre's theorem on it. Okay, so if we think about what this looks like, we're in the positive quadrant, we're across by k root 2 and up by k root 2 on the imaginary, which puts z to the 4 just here. Now putting that into polar form, we need a length and an angle. Well, the angle is 45 degrees, which is pi by 4. So z to the 4 will be equal to a modulus and then cis of pi by 4. Now the length of it is using Pythagoras, so the modulus of z to the 4 will be equal to the square root of k root 2 squared plus k root 2 squared. So that's going to be the square root of k squared, or rather root 2 times root 2 is 2, so that's going to be 2k squared plus 2k squared. That's the square root of 4k squared, so that is equal to 2k. So our modulus here is 2k. Okay, now on to using de Moivre's theorem to find the roots. So the first root is by doing 2k cis pi by 4 to the power of a quarter. Now the modulus gets put to the power of a quarter, so that's the fourth root of 2k, and the argument gets divided by 4, so this will be pi by 16. Now once we have the first solution, all of the others are equal distance around that diagram. Now if we have 4 solutions because we are doing an equation to the power of 4, we know that those 4 solutions will be evenly spaced around there. So each of them will be 90 degrees on from the last one, which is another pi by 2. So the second solution will be to add on pi by 2, which is the same as saying it's the fourth root of 2k because the modulus never changes. But if we do 1/16 plus 1/2, we get 9 pi by 16. Now the third root, I'm just going to go over and look at the diagram because that's going to end up being over the pi line, which means we actually want to take it under and make it negative instead. So we'll go from this one through there. So this will be fourth root of 2k, cis of pi by 16, take off 180, which is pi. So 1/16 take away 1. This will be 4 root 2 cis of minus 15 pi by 16. Just give myself a little more space for the next one. So z to the 4, fourth root of 2k cis, and this one will be taking us from the first solution just back by one lot, so back by 90 degrees or pi by 2. So that'll be pi by 16 take away pi by 2. So 1/16 take off 1/2. It's going to be minus 7 pi by 16. Okay, last question. As is often the case with locus, let's start by saying z is equal to x plus iy. Z minus v is x plus iy minus 3 plus 2i. For x minus 3 plus y minus 2i. The argument of this thing places it over here with an argument of 3 pi by 4. Now that is at a position of x minus 3, y minus 2. But the x minus 3 is on the negative portion of that axis. Now, since this is 3/4 pi, it makes this bit here a quarter pi, or 45 degrees, which means we've got an isosceles triangle. So y minus 2 is equal to minus x minus 3 in length. plus 2 equals minus x plus 3. So y is minus x plus 5 as the locus that we are looking for. So any point that is on this line here is going to satisfy this situation that we had in the question. Okay, that's it for this set of answers for the worked solution booklet for complex numbers. I am also doing the ones for integration and differentiation. If you're looking for worked solutions to those D&D books, check out the homepage on my channel and you'll be able to find what you're looking for.